Okay, so today's class is a little catch me up or review in some cases on the topic stress. So we want to just be able to start week 5 fresh with a discussion on the digestive system. So we're going to fill in this time with our recording of the topic stress. So we can define stress as one way to define stress is it's some sort of abnormal homeostasis. And more specifically, it's a real or perceived threat to homeostasis. And we can describe acute stress as eustress and long-term stress or chronic stress as distress. And most of our systems are built to resist or respond to eustress. They're responsive. Remember, that was a characteristic of living organisms. They have responsiveness or adaptability. So that's what's happening during acute stress. It usually indicates that this is temporary, and often we come out of that better than we went into it. So it results in growth or strength, that sort of thing. So that's what happens when you go into the gym and you lift weights. That's a stress to the muscular system and somewhat to the skeletal system. And the fact that it's temporary promotes growth and strength. Distress, on the other hand, often leads to exhaustion, injury, or at least depletion. And we're going to see how we can often end up with a pathology as a result of being exposed to chronic stress. So there's another term that we'll just mention while we're on the topic of terminology here. Allostasis is a variation on homeostasis, and anytime that our body is in a state of adaptation or resistance to a stressor, we refer to that as allostasis. That's a process that attempts to achieve we're attempting to achieve homeostasis or meet new demands with compensation. So we can appreciate here that what we're talking about is recruiting energy and function in order to meet these new demands. So this might be what happens. Most of us, if we've ever gone for a training run, let's say you're going to run for 3 or 4 or 5 kilometers, in that first few hundred yards, you feel out of breath and your legs feel heavy, and you think to yourself, well, there's no way I'm going to get through the next couple of kilometers. And then you establish a new base level. Your breathing gets more even. Your energy levels have risen to meet the new demands, and you get into a pattern that allows you to complete that kind of challenge. So that would be allostasis. Your heart rate is no longer at a resting rate that we know is somewhere between 60 and 90 beats a minute. It's probably going to be at 150 or 120 to 180 beats per minute, that sort of thing. So again, allostasis is typically temporary and often results in decompensation if it goes on for too long. So we'll just, uh-oh. In other words, we can't run forever. We're going to decompensate. We're going to run out of energy stores, and that's going to force us to stop. So all of this stuff about stress, or not all of it, but a lot of it, was researched and clearly described and explained by a guy named Hans Selye. Hans Selye was born in Hungary but did his research in Canada. Most of it, I think, he did at McGill University. But he is sometimes nicknamed the stress guy, and that's because he's the one who really described the stress response and clearly identified what goes on during the stress response. And he coined the phrase general adaptation syndrome. So he divided the stress response into 3 stages. The first stage is our alarm stage. And I think by now most of us are well aware that during the alarm stage, the primary system that's going to be involved is the sympathetic nervous system, that division of the autonomic nervous system that's responsible for fight or flight. So we're going to get during this stage the activation of the hypothalamic anterior pituitary axis, which is otherwise abbreviated HPA, and the result of that is going to be the release of, among other hormones, cortisol. And cortisol has been nicknamed in the past as our stress hormone. It's the one that we can point to that's going to result in a lot of the decompensation that goes on during a chronic stress situation. In the second stage, it's known as the resistance stage. This is where compensation is going to occur. This is where mechanisms are going to be recruited to meet the longer lasting stressors. This is also known as adaptation. Allostasis is really what's going on in this second stage, that term that we mentioned in the previous slide. And if the stressor is not removed, is not dampened in some way, we're going to lead to the third stage of the stress response, which is exhaustion. And in exhaustion, we're saying that all of our energy resources have been depleted. And normal functions, including the resistance phase, allostasis, are failing. So this is what we refer to as decompensation. And this is the step where it will often manifest as an illness. Will end up being represented by some sort of a pathology. So and we recognize that there's what's sometimes called a pathological triad. So that results, you see that word triad, you should recognize that there must be three things going on. One of the things that we notice in this triad that represents ultimately decompensation is that we get hypertrophy of the adrenal glands. The adrenal glands are the glands that are responsible for producing cortisol. So we're going to get hypertrophy of those glands because we're signaling for a response against the stressor. But that chronic high level of cortisol results in atrophy of our lymphoid tissues. And our lymphoid tissues are locations for much of our immune cells responsible for protecting our body from infections and other types of antigens. So if we have a atrophy of those tissues, we're going to have a dampened or reduced immune response. And the third thing that makes this a triad is it's not uncommon to see gastrointestinal ulceration. High levels of cortisol will create an imbalance of the secretions in the stomach in the favor of acids, and the acids will start to erode the mucosal membranes of the stomach, and we get an ulcer. That's particularly likely to happen in the stomach, but could also happen in the small intestine as well. So those are the things we're concerned about with chronic stress, is leading down to that exhaustion stage. So it makes sense that we spend a little bit of time looking at this hormone, cortisol. And this sort of goes hand in hand with what your written assignment is going to be about when we look at this scientific paper and pick some sort of a chemical messenger, a signaling molecule, and look at all of its functions and what might happen in the absence of that chemical messenger. So in the case of cortisol, we know that cortisol has a direct effect on the immune system, and that immune system is going to be suppressed. So how it does this is it's an anti-inflammatory, so right away we know that the inflammation response is usually one of the first steps in an immune reaction. It signals the rest of the immune system to become active. But it also inhibits white blood cell formation. So during an infection or an attack by any type of antigen, we expect to see an increase in the mitosis of specific white blood cells that are designed to help with phagocytosis and with recognition. And if those cells are down in numbers, then we're going to have less of an immune response and become more prone to illness. Now, cortisol also does many other factors. It's also hyperglycemic. It promotes protein breakdown and lipid breakdown to make those building blocks, amino acids and fatty acids, available for gluconeogenesis. Remember that process, gluconeogenesis, is creating glucose, or at least pyruvate, to be made available to the mitochondria in order to be able to make lots of ATP. So this immediately doesn't look like we're making glucose or becoming hyperglycemic with these two functions, but because we have the amino acids and fatty acids available for gluconeogenesis, we spare the glucose. Therefore, blood glucose goes up. And now so this is the mechanism behind how we're going to raise blood glucose levels under the influence of cortisol. Now, when you look at these two factors, protein breakdown, lipid breakdown, if that's going to go on chronically, what happens is we lose some of the stored forms of these amino acids and fatty acids, and then we have to take from established structural components in the body. So lipids will be easily mobilized from adipocytes, but once those sources are depleted, we're going to have to take fatty acids from other places, and we may have to redirect some of the fatty acids that would normally go into mitosis for cell division and use them instead as a source of energy. Protein breakdown might mean that we're going to see some muscle wasting or some bone osteoporosis, for example. So we also know that prolonged high levels of cortisol decrease calcium absorption. Therefore, we're going to get decreased bone mass. We get muscle atrophy. And all of these are related, muscle atrophy in particular, to this protein breakdown that's going on. And we know that chronically high levels of cortisol interfere with sleep cycles as well. Now, situations that are known to lower cortisol include exercise, particularly after the exercise, because during the exercise it's a stress, so we'll have elevated levels, but then we get a dramatic reduction in cortisol on the recovery phase, so that's beneficial. Maybe we'll just make sure we understand that it's after the exercise here. We know that massage will reduce the levels of cortisol, music, and there's some other things like meditation, for example, and other factors that are behavioral factors that can reduce the requirement for So when we have I'm just summarizing what we're doing with the immune system. If we reduce the inflammation response, reduce the white blood cell response, we're going to reduce resistance to any antigens, so particularly infections, and we're also going to inhibit tissue repair. We reduce repair, Because as we know from what we talked about a week or two ago, inflammation is the first step in the repair process. Unless, of course, you chose to Google it, and then the first thing that comes up in Google is the reversal of those steps. It talks about hemostasis being first and inflammation being second. That's a little giveaway that some people use a little cut and paste technique there for looking for that particular answer. So what's the pathway? Remember we said that we activated the HPA axis, the hypothalamic anterior pituitary axis. So if we're going to look at what that axis looks like, we better start with the hypothalamus. And we know the hypothalamus is the location in the central nervous system where integration for the autonomic nervous system occurs. And it's also the location where we have a direct communication between the nervous system and the endocrine system. And that communication occurs between the hypothalamus and the pituitary gland. For the stress response, we're particularly interested in the anterior pituitary gland. The hormones that are going to be released in response to stress will come from the anterior pituitary gland. So let's follow cortisol. From the anterior pituitary gland, we're going to target the adrenal gland. We know by the name adrenal that it sits on the kidney. The name itself tells us. And there's a hormone that's called corticotropin releasing hormone that stimulates cells in the anterior pituitary gland to release adrenocorticotropin, or ACTH. And when ACTH targets the adrenal gland, we're going to get the release of cortisol. In fact, what I'll do is keep ourselves color coordinated. So that's our direct pathway to get to our stress hormone. And we're going to get an increase in the release of cortisol. So we know that the result of that is going to be some protein breakdown, some lipid breakdown. So some people might say, well, that sounds a little bit like weight loss. Maybe that's a good thing. Well, we know that on a short term, it might be considered a good thing, but long term, it becomes decompensation. Decreased inflammation, decreased immune responses generally. And we're going to see some gluconeogenesis. So we're going to get an increase in gluconeogenesis. So all of those things are going to be part of our pattern of activity when we look at the stress response and what's going to ultimately lead us to exhaustion. So we're also going to take a look at growth hormone, releasing hormone that comes from the hypothalamus and targets the anterior pituitary gland to release growth hormone. And when the growth hormone is released from the anterior pituitary gland, it's going to target the liver, and the liver will release what are called IGF, insulin-like growth factors. Insulin-like growth factors target most cells in the body, and they promote a little bit of lipolysis, but they promote protein synthesis. So in this case, when you think about growth, we expect to see some protein synthesis. So growth hormone is responsible for what we call lean body mass. Growth hormone has become a popular um, designer drug, if you like, for the rich and famous in the United States because they believe it to be a youth drug. They use it as a youth drug. And when they take growth hormone, it promotes protein synthesis, so muscle, at the same time promoting lipolysis, weight loss. But it, of course, has some side effects as well. Breaks down glycogen, so that is known as glycogenolysis. Genolysis. Okay, and when we increase glycogenolysis, we're going to make glucose available. So both these last two items here are responsible for raising blood glucose levels during stress. We want that. That's a positive response, but it leads us to exhaustion. Then we want to look at the third hormone that gets released during the stress response. And that is TRH to TSH to T3 and T4. The thyroid hormones that get released. And when the thyroid hormones get released, we know that they increase oxygen uptake in almost every cell in the body. And when they increase oxygen uptake, they make oxygen available to the mitochondria to make lots of ATP. So that's all about increasing ATP, also known as increasing the basal metabolic rate. Again, fits with fight or flight, right? But this is the endocrine response now, so it's a little slower but longer lasting. But also promotes lipolysis and proteolysis. So prolonged long-term T3, T4 elevation is going to ultimately end up promoting protein and lipid breakdown. So this is the endocrine response to this hypothalamic anterior pituitary axis that is a response to the stressor that is hanging around for a long time. Now, we mentioned at the very beginning that during the alarm stage, it's a sympathetic response. So we can draw a sympathetic response in here as well. Let's find a color that's going to give us our sympathetic response. Remember, integration for the sympathetic nervous system occurs in the hypothalamus, so we can draw this down to the sympathetic response. And when the sympathetic response is activated, it targets the adrenal gland directly. So the neurotransmitters from the sympathetic division target cells in the adrenal gland and encourage the adrenal gland to produce epinephrine and norepinephrine. Epinephrine and norepinephrine are the same neurotransmitters released from the sympathetic division of the autonomic nervous system, but now when they're released from the adrenal gland to target receptors in the body, they're acting as a hormone. It's the same substance. In the nervous system, it acts as a neurotransmitter. In the endocrine system, it's acting like a hormone, but it's going to promote the same responses as fight or flight. So we will see an increase in heart rate. We see an increase in respiration rates. And that comes at least partly from bronchodilation. We get an increase in blood pressure. And we get an inhibition of GI function. We know that from what we know about during the fight or flight response. So this is what's going to lead us to ulceration. in combination with the prolonged elevated levels of cortisol, we're going to get both things contributing towards this ulceration function. So chronic stress is going to lead us to distress due to the prolonged elevated levels of cortisol and the prolonged elevated sympathetic response. So during adaptation, the change in physiology and our behaviors in response to these altered stimuli, the stressor, results in elevated heart rates and an increase in blood pressure, and those factors long term become dangerous. So they're going to ultimately lead to exhaustion. We can't maintain those levels. So what do we do in stress generally is we try to establish coping mechanisms. So most of us are generally aware of mechanisms that are important. Positive ones or good mechanisms are some of those things we just mentioned a few minutes ago: exercise, music, meditation, all things that really represent a bit of a distraction. Now, some people also go through some bad compensations. In other words, compensations that are not going to help with the stress response. They're not going to help improve your situation. So that might include eating, smoking, or simply avoidance. In other words, just trying to ignore the stressor altogether. That's not going to lead to much of a change in behavior and not going to lead to a change in the stress response. So coping typically is behavioral as well as some physical approaches to dealing with the stressor. And we're successful when the mechanisms reduce the conditions or the feelings of stress. If it's an ineffective type of coping mechanism, then it may just lead to a worsening of the situation. So what causes stress? Because there's a perceptual component, individuals will respond to stressors in different ways. So some things that might stress one individual would not be a stressor for another individual. If it's a physical stress, that's a fairly standard type of challenge, but the psychological stressors can be quite variable. So causes of stress are variable, and they can be subjective or objective. So they can come from physical or environmental sources. They could be just the same sorts of things we talked about that can cause cellular injury. Biological factors would include our viruses and our bacteria. But we also have emotional factors that can play a role. And those might be influenced by things like our culture, social That's not very. And psychological. So lots of factors are going to play a role in what becomes a stressor. So treatment. Our first option in any kind of treatment for stress is to try to identify the cause, just like we talked about when we looked at infections. Identify the cause and then take steps to either remove, and if that's not possible, reduce the source. Remember, our progression went from an acute to a resistance to exhaustion in a continuum. First stage, second stage, third stage. So it's a continuum getting from what can be actually beneficial, acute, to acute phase typically was temporary. Okay, and then we were leading down the scale towards chronic. So treatments that are beneficial, massage, and exercise, we've talked a fair bit and will for the rest of the semester, especially with rest periods built into that. Music therapy, one of the bases behind the exercise factor is that those enkephalins, endorphins, remember those were our natural opioids, give us some benefit. And avoidance of, let's see, release of natural opioids. And then, of course, where possible, avoidance of known stressors. So if you know of stressors, if you know of triggers that are going to activate your general adaptation syndrome, you avoid those where possible. And obviously, lots of scenarios where that's not possible. Life is a stressor. The fact that we are alive and get up every morning and challenge our bodies to walk or run or study, whatever those all represent stressors. Anything above the resting level is by definition a stressor. But when we cope and when we train, we get better at minimizing the negative effects of those stressors. And that's our goal in life, is to try to minimize those stressors in order to maximize growth, development, and responsiveness.